Dear students, welcome to the video, the Poisson distribution. In probability and statistics 1, you learned about discrete probability distributions. In the binomial distributions, there are fixed number of trials denoted by n with only two possible outcomes, usually designated success or failure. Success was denoted by P and failure was denoted by Q for each trial. And you count the number of successes. In the geometric distribution, there are again two possible outcomes, success or failure, and you count the number of trials up to and including the one in which the first success is obtained. Now consider the examples in which you count occurrence of an outcome, but the situation doesn't fit either binomial distribution or geometric distribution model. First case, the number of soldiers in the army accidentally killed by horse kicks in a period of time. A second case, people with severe insect bites attend a clinic in a period of time. A Poisson distribution can be used to model a discrete probability distribution in which the events occur singly, at random and independently in a given interval of space or time. The mean and variance of a Poisson distribution are equal, hence Poisson distribution has only one parameter. When modeling data using a Poisson distribution, work out the mean and variance and check if they are approximately equal. If they are not approximately equal, the Poisson distribution is not a suitable model to use with the data. Use the mean to calculate probabilities and expected frequencies. The third one, compare expected frequencies with observed frequencies. If the random variable x has a Poisson distribution with parameter lambda, where lambda is greater than 0, we write lambda has Poisson distribution with lambda as parameter. And probability of x is equal to r will be equal to e to the power of minus lambda, lambda to the power of r over r factorials, where r can take the values of 0, 1, 2, up to infinity. Expectation and variance are the same as it was mentioned in the previous page, and both are equal to lambda and denoted by lambda actually. So we have actually one parameter denoted by lambda. First example, the number of calls to a consumer hotline is modeled by a Poisson distribution with a mean call rate of 6 per minute. So lambda is equal to 6 per minute. Calculate the probability that in a given minute there will be part A 9 calls, B 3 or fewer calls, C more than one call, and D at least one call. So as given in the question, X has Poisson distribution with parameter 6. Now the first part A, it says 9 calls. So you are supposed to find probability of x is equal to 9. We know that probability of x is equal to r is equal to e to the power of minus lambda lambda to the power of r over r factorial. Now here in this case r is 9 and we already know that lambda is 6, so it will be e to the power of minus 6 to the power of 9 over here 9 factorial, which will be equal to 0.0688. Now part B, it says probability of 3 or fewer calls. So probability of x less or equal to 3. So x could be 0 or x can be 1, or x can be 2, or x is equal to 3. Now is equal to x is equal to 0, so it will be e to the power of minus 6. 6 to the power of r in this case is 0 over 0 factorial plus e to the power of minus 6. Here 6 to the power of 1 over 1 factorial plus here e to the power of again minus 6. 6 to the power of 2 over 2 factorial plus e to the power of minus 6, 6 to the power of 3 over 3 factorials, which will be 0.15 and 1. Part C, it says more than 1 call, so probability of x greater than 1. So as you know, in Poisson distribution, r can take values from 0 up to infinity. You cannot count all the numbers greater than 1, but what we can do to write 1 minus probability of, we actually calculate the left hand side, less or equal to 1. So it will be 1 minus probability of x is equal to 0, or probability of x is equal to 1. So it will be 1 minus probability of x is equal to 0. It will be e to the power of here minus 6 to the power of 0 over 0 factorial plus e to the power of minus 6 to the power of 1 over 1 factorial, which will be 1 minus 0.0174, giving you an answer of 0.983. And for the last part, which is part D, it says probability of at least one call. At least one call means 1 or greater than 1. Likewise, we cannot calculate all the probabilities for cases greater than or equal to 1. So what we can do to write 1 minus probability of x less than 1, which is just 0. So it will be 1 minus e to the power of minus 6, here 6 to the power of 0 over 0 factorial, which will be at the end 0.998. Example number 2, a typesetter makes on average 5 errors per page of typing. So lambda is 5. Part A is state the assumption made to model the average number of errors per page as a Poisson distribution. So we know that in order to have Poisson distribution, we need to have these properties. First, errors should occur first independently, then singly, and at random. Part B, it says in a book with 200 pages, on how many pages would you expect to find at most 2 errors? So we know that X has Poisson distribution with parameter 5. Now we already know that probability of X is equal to R is equal to e to the power of minus lambda to the power of R over R factorial. R starts from 0, 1, then 2. Now it wants you to find actually at most 2 errors. So first, let's calculate the probability of x less or equal to 2, because it says at most 2 errors. So it will be 0, 1, 0, or 1 or 2 errors. So it will be equal to here in this case r is 0, so it will be e to the power of negative 5, 5 to the power of 0 over 0 factorial plus e to the power of negative 5, 5 to the power of 1 over 1 factorial plus e to the power of negative 5, 5 to the power of 2 over 2 factorial, which will be 0.12465. Then it wants you to find the number of pages in 200 pages. So to find this expectation, so you multiply 200 by the probability of less at most 2 errors in one page. So probability of at most 2 errors in one page is 0.12465. So in 200 pages, it should be multiplied by 0.12465, which will be 24.9 or 25 pages.